In this video, we're going to discuss the line spectrum. So as light passes through a prism, it gets refracted or bent. The angle of refraction depends on the wavelength of the light. So incoming light essentially gets separated into its component waves based on the different wavelengths. White light is made up of all the different colors of the visible spectrum. So when we pass white light, something like sunlight, through a prism, it gets separated into what we call a continuous spectrum, which shows all the different colors of the visible spectrum. By heating a gas, such as hydrogen, with electricity, it will also give off a color. If we pass the light through a prism, it gets separated into its component wavelengths. So an experimental setup for that might look something like this. Here we have a discharge tube, which is basically a light bulb. If we put hydrogen gas inside that tube and we run a high voltage electric current through there, then the hydrogen gas will give off a light. Pass the light through a slit and then pass the light through a prism, and the light given off by the hydrogen gas will get separated into its component wavelengths. We would see that for hydrogen gas, we get 4 distinct lines, which indicates that the light given off by hydrogen gas is made up of 4 different wavelengths. If we look at this through an instrument called a spectrometer, we can measure the wavelength of each of these spectral lines for hydrogen. So each element gives off its own distinct colored lines when we pass them through a prism, and we call these spectral lines the line spectrum. The line spectrum can be used to identify a particular element. Here you can see line spectrum for several different elements. Here's hydrogen. If you put lithium gas in a discharge tube, passed it through a prism, we would see that the light given off by lithium is made up of 4 distinct colors. And so the line spectrum for lithium you can see is unique or distinct from any of the other elements. So line spectrum for various elements had been observed for years, but it really wasn't until the Bohr model came along that scientists could explain what was going on, how the line spectrum were formed. So how does the Bohr model, or today's quantum mechanical model, explain an atom's line spectrum? Well, let's look at a hydrogen atom as an example, since it's a very simple atom. And before we start, remember that the Bohr model predicted that the energy of electrons was quantized. That means that electrons are only allowed to have certain distinct energies around the nucleus. So therefore, electrons are only allowed to occupy certain orbits or shells around an atom. The electrons cannot exist in between these shells. So let's take a look at hydrogen's line spectrum. And to do that, we're showing you here the different shells represented by these lines here. So this is the first shell, and this is the energy of the first shell, the second shell, and the energy of the second shell. And the energies are expressed in electron volts. Electron volts is just a unit of energy, similar to joules. You can see the conversion here. But the electron volts are just a little easier to work with for this particular application. Also, you can see that as we get further from the nucleus, the energy of the shell increases. So hydrogen has 1 electron, and that electron begins in the first shell. This is what we call the ground state. This is the most stable, lowest energy shell occupied by an electron. And remember, electrons can only gain certain quanta of energy. A quanta of energy is basically what we call a photon. So electrons can only absorb photons with certain energies. To get an electron to absorb a photon of energy, we could heat it, run an electric current through there, bombard it with electromagnetic radiation, or some other methods. So our photon, our hydrogen electron can only absorb photons with energy equal to the energy difference between shells. Now this is very important. Remember, electrons cannot exist between the shells. So for example, if we took an electron from the first shell to the second shell, we would have to zap, or that electron would have to absorb a photon with exactly 10.2 electron volts. This is equal to the difference between the second and the first shell. If an electron went from the first shell to the third shell, it would absorb a photon with exactly 12.1 electron volts. In other words, the difference in energy between n equals 3 and equals 1. The electron in hydrogen or any other atom cannot absorb a photon or a quantum of energy that would put it between two shells. So for example, our electron in hydrogen could not absorb a photon of energy with 2 electron volts, because that would put it somewhere in between the first and the second shell. So when an electron absorbs energy and jumps from one shell to a next, we sometimes call this a quantum leap. But again, the electron cannot exist between shells or orbitals. So it does something very strange. The electron essentially disappears from the first shell and reappears in the third shell. So an electron that has absorbed a photon of energy and is now in a higher energy level than its ground state is said to be in an excited state. The excited electron is of course drawn back to the nucleus or its ground state, and so it wants to relax or fall back down to its ground state. Because the electron's energy is quantized, it must release energy as it appears back in its ground state or in a lower shell. When the electron falls from the higher energy shell or orbital to one closer to the nucleus, the energy given off is emitted as a single photon of light. Now that's important. So let's look back here. Our electron absorbed a photon and jumped from n equals 1 to n equals 3. And now let's say that electron fell from n3 to n2. The electron, to get from n3 to n2, it cannot just fall back down. It must disappear from the third shell and reappear in the second shell. As it does this, as it undergoes this transition, it must release a photon of energy. Because if it falls to the second shell, it cannot still have 13.1 electron volts. It must have 11.2. So as our electron falls from 3 to 2, it essentially disappears from n equals 3, reappears in n equals 2, and it releases a photon, and the energy of that photon is equal to the energy difference between the shells, similar to what we said when it was absorbing energy. So if it fell from n3 to n2, it would disappear, reappear in n equals 2, and it would release a photon with 1.9 electron volts of energy. Now that's very important for you to appreciate, so be sure you're clear on that. So that photon would be released. If we measure that with a spectrometer, it may give a band or one of our spectral lines for the line spectrum. So only certain photons can be released. Some photons, as they're released, fall within the visible spectrum. So as our electron goes from 3 to 2, it releases a photon with 1.9 electron volts, and that happens to fall within the visible spectrum. So we could detect that photon or that wavelength of energy being given off as a red spectral line. Now there's a relationship between energy and wavelength that we need to be sure we appreciate. The energy of a photon is equal to hc over lambda. So essentially, the energy of a photon is inversely related to its wavelength. So what is hc over lambda? Well, E, of course, is the energy of the photon in units of joules. H is something called Planck's constant. You can see the value here. C is the speed of light. And lambda is the wavelength of the photon released in meters. So let's try a problem here. Take a look at this problem, and let's say our electron starts in an excited state, n equals 5, and it falls to n equals 2, all in one, let's say, quantum leap. It goes from n5 to n2 all in one leap. See if you can calculate the energy of this photon and calculate it in units of joules. Then see if you can calculate the wavelength of that photon. Pause the video and give it a try. Okay, so as our electron goes from n equals 5 to n equals 2, it must release a photon of energy. It must release a single photon, and the energy of that photon would have 2.9 electron volts of energy. That would be the difference between the fifth and the second shell. We could convert that to joules using our conversion factor. Our electron volts go on the bottom, and our joules go on the top. We multiply, we get 4.6 times 10 to the negative 19 joules. So that would be the energy of our photon. Now what about the wavelength? Well, if we need to relate energy and wavelength, we would use our equation here. I could rearrange that to solve for wavelength. It would look like this. So if I plug in Planck's constant, the speed of light, and my energy, I could solve to get the wavelength. Now one thing before we move on, be sure that when using this equation that your energy is in joules, because we need our joules to cancel and our seconds cancel, and we would end up with our wavelength in meters. If you're given a wavelength, be sure that it's in meters in this equation. So solving this, paying careful attention to our units, we get the photon released would have a wavelength of 4.3 times 10 to the minus 7 meters, or 430 nanometers. So one last bit of information that we want to look at with line spectrum. For a hydrogen atom, an electron can undergo any different number of transitions. It could fall from n equals 2 to 1, n equals 3 to 1, etc. So if the electron falls from any higher shell down to the first shell, it will give off a photon, which generally falls within the ultraviolet range. So we can't see these transitions with our eyes. These aren't part of the line spectrum, but we call these the Lyman spectra, the Lyman series, when an electron in hydrogen falls from a higher shell down to the first shell. If an electron falls from a higher shell down to the third shell, it gives off, each of these transitions would give off a single photon, which would fall in the infrared region. Again, these would not make up our line spectrum because they're not in the visible range, but these are called, these photons that are given off are part of the Paschen series. Now, if an electron falls, let's say, from the third shell to the second shell, it gives off a photon which does fall in the visible range. It would give off a light which is red, and the wavelength would be around 656 nanometers. If the electron fell from 4 to 2, it would give off a green spectral line, a photon which had a wavelength in the visible range, and the wavelength would have about a 486 nanometer wavelength. From 5 to 2, you can see here, we'd end up with a blue spectral line. From 6 to 2, we would end up with kind of a purple spectral line. And from 7 to 2, again, we would be out of the visible range here. But all of these, where the electrons fall from a higher shell in hydrogen to the second shell, these are what make up the Balmer series. And these constitute our line spectrum. So be sure you're familiar with these, the line spectrum. Be sure you really appreciate how the line spectrum demonstrates the quantization of energy. So look over that, be sure you're familiar with these terms, and also be able to solve some of these mathematical problems.